Morning. It seems like everybody is in jet lag. Anybody here from the US, happy Thanksgiving. This is the first time for me to present my work on a Thanksgiving break, but I hope you enjoy what we're going to present. My name is Amir Bezadan. I'm Associate Professor of Construction Science from Texas A&M. My colleague here, Theodora Chastari from Computer Science at Texas A&M is a collaborative of mine. And my student Nippon is the person who actually did the research. So I'm going to present some of his work here, and then hopefully we have time for some discussions at the end. I would like to start with just an infogram. The amount of digital photos that we have been taking since the past 5 years has been doubled. And that's thanks to the invention and the advancement of digital tools such as smartphones, tablets, and what have you. But the problem is we're not using them efficiently, especially in construction, despite there is a value for using images and videos. For example, I have some cases here. We can use a lot of images and videos for progress reports, for requests for information, documentation, safety training, productivity monitoring, and claims and litigation. But most of the times, the images, videos we take are remain unused or archived without really proper use. So what are some of the challenges? Why can't we use these images? First of all, we have a lot of them. We just randomly take photos as we walk on a street or on a job site with a smartphone. We don't end up using them efficiently. Most of our images, although they are very semantically rich, only contain, when you look at the file of a JPEG file or a TIFF file, the file only contains date and time information. If you are fortunate enough and use your smartphone while the GPS sensor is on, then the file also have a geolocation attached to it. But that's pretty much all the information an image will give you once you take that image. And that makes it very difficult to retrieve information of other types. For example, if you want to know what objects exist in that image, or what was the weather condition, what was the humidity, what was the temperature, what was the ambience, what was the context in which that image was taken, that's very difficult to retrieve manually. So a solution obviously is to create metadata tags, and then these are the tags that explain the content, explain the context, appearance of the image. Again, because we have a lot of images and videos, manually doing this is very difficult, and therefore a solution that enables automated generation of these metadata tags seems to be very promising. So here are some examples of images that have been taken from construction job sites, and in each image, the object of interest could be tagged as part of the metadata tagging. A look at the current literature, which is mostly done outside the domain of construction, shows us there are work out there where people actually tag objects, and there are algorithms in machine learning and computer vision that help you tag these images automatically. Most of the current literature, despite of that, most of the current literature talk about everyday objects like cats, dogs, horses, frogs. Those are not really relevant to construction. In construction, there is a limited amount of work, if any, that deals with this problem. There is some work, however, in which people have tried to tag workers, excavators, guardrails. Most of them use traditional machine learning, which requires features to be handcrafted, selected, ranked, and then used. So in traditional machine learning, as I said, you have to carefully investigate your digital content and then find out what features represent those content the most properly. And then the problem with that is that it's not scalable. Once you find out the features associated with a certain visual data set, it is very hard to apply the same set of features to a different data set because your features are very much associated with your visual content. And therefore, it creates a very computationally intensive process. What we are doing in my lab is we are using deep learning. So in deep learning, what the model does is that it self-learns from the content. You don't have to feed it with a set of features. It actually does a very fast brute force and then finds the features that best represent your visual content. Therefore, it's generalizable. You can train it on a certain data set and then use it on a different data set because almost all features are considered. And that creates a lot of flexibility in representing the content of your visual data set. So essentially what deep learning does is that it eliminates this step of feature extraction and classification. It brings everything together in a deep learning model. So just like a very high-level overview of what how deep learning looks. Obviously, if I give you an image and you want to learn from that image, ideally you would like to go through the pixel by pixel representation. So each pixel of that image on the top left side will be fully connected to the layers of your neural network. However, this is very computationally intensive. So in reality, what we do is that we pick convolutions or regions within that image and then study each region and then try to connect those regions to the nodes of your neural network. Or you can look at each region or convolution and then find a weighted average of the importance or significance of that region and use a weight sharing in your model. And then eventually your model is developed more by adding more layers that do max pooling and more convolutions until you get to a point where you can decide what content that image has. So like I said at the very beginning of my talk, in construction, historically, we have been very reluctant to change. And technology is a huge change in construction. So when it comes to deep learning models, computer vision, machine learning, there are not too many data sets around that are publicly available for researchers and practitioners. And those data sets that are available are usually not labeled. They're just, you have videos or images, they're not labeled properly for a certain application. So again, we have to go through all the data set and create our own labeled data set. That creates a very difficult task. And the amount of the images and videos that are actually of good quality for us to use is very limited. So the solution we came up in our research was to use transfer learning. In transfer learning, we take a model that is pre-trained on a different data set, and then we try to modify it and adapt it for our own data set. Specifically for our research, we're using VGG16 or OxfordNet, and that is one of the best performing convolutional neural networks out there. It has 16 total layers, including 1 input, 13 convolutions, 1 fully connected, and 1 output layers. And then it has been trained on 1.2 million images that represent 1,000 classes of objects. So we don't have to do anything about that. All we do is that we take that and then we adapt it for our application. This is what we do in transfer learning as applicable to our research. The top side shows the training step. We take VGG16, we use the layers of VGG16 as the first layers of our neural network, and then we add 2 more layers to represent our specific needs in our visual data set. So in total, we have 18 layers. We take 80% of our image data set and use that for training, and the remaining 20% is used for validation. Now, specifically to our project, a description of our data, we have collected data from using web mining, specifically through Google Images, and we use keywords that are listed here: building under construction, construction equipment, construction worker, and we collected our images, and then we use label box to tag each image using a single label as either representing a building, an equipment, or a worker. So this diagram shows a breakdown of the images that we have in our data set. We have about 1,600 images representing buildings, 1,400 images representing equipment, and 1,100 images representing workers. And also the diagram shows how many of these images in each class were used for training versus validation. Like I said, 80% of each image of each class was used for training, 20% was used for validation. Because we're using transfer learning, we are limited by the requirements of VGG16 specifically. Most CNN models require square size images. So in case we ended up collecting an image from Google Images that is not of a square size, we had to come up with a method that breaks that image up into a number of square images. So that's a pre-processing that we needed to do on our images. And then the resolution that is used by VGG16 is 128 by 128 pixel in each dimension. So we had to also work on those resolution requirements to make sure our images meet the VGG16 requirements. This is an overview of how our model works. Obviously, I don't expect you to see exactly what's going on in each of these pixels, but essentially we start with an actual image, as I said, 128 by 128, and then we take that image through a series of convolutions and max pooling layers in our deep neural network model. And then at the end, we tag that image as either building, equipment, or worker with certain probabilities. So in this case, the image that was fed into the model turned out to be a building with 99.9% confidence. Quick overview of the results. So like I said, our model is based on VGG16. It's a transfer learning model. And it's pre-trained on ImageNet dataset, the 1.2 million images, like I mentioned. And we fine-tuned the model with our own dataset that was a collection of the building equipment and worker images. The baseline model we used to benchmark the performance of our model was a CFAR-net that is also a commonly used deep neural network model in computer vision. And this model was trained on its own dataset and was trained from scratch. So the diagram on the top shows the performance of our model compared to baseline model in terms of precision and recall, and for different tags, including building, equipment, and worker. And as you can see, we can outperform CFAR-net by a few percentage points. Also, I would like to talk about some of the limitations or maybe some of the constraints of the model. So for that, what you see on top is a confusion matrix. Confusion matrix is a very good visual representation of how well a model performs. In a confusion matrix, the diagonal shows the recall or the accuracy of your model. So for example, in our case, if we mark the image as a building, in 95% of cases, the image was predicted as a building, so our model was 95% accurate when it came to detecting buildings. Same for equipment, 89%, and worker, 89%. Now, when you process an image in a deep neural network, what happens is that the model looks at the entire content of the image, the entire content of the 120 by 128 image, and then it finds out what is the predominant visual content of the image. So imagine you take an image of a worker on a construction job site, but the worker is standing in the foreground and there's a huge building in the background. A human eye can detect or can understand that the focus of the image was on the worker. But a computer vision model sees the big building in the background and assumes that you actually meant to take a photo of the building. So that may create confusions when it comes to detecting objects of interest in these images. So some of these confusions can be seen here. So for example, if you look at the rows of the confusion matrix, the rows represent recall numbers. You can see that some of the workers were identified as equipment or buildings. So in 11% of cases, we identified equipment and buildings for images that were meant to be from workers. And that reduces the recall a little bit to 89%. Similarly, when you look at the columns of the confusion matrix, the columns are good representative for precision. So in this case, some of the equipment and worker objects were detected as building. And that creates about 14% inconsistency in the prediction. So that reduces the precision a little bit. So like I said in this presentation, the goal of this research so far was on single tagging of images. But what is next? Obviously, when you take a photo in a construction job site, you might have multiple objects of interest in that photo. So we're working on multi-label annotation of construction job site photos. We want to have a fast method, which means 30 frames per second or more, so that we can do this in real time, not just on images, but also on video feeds that we receive from construction job sites. And we are increasing our dictionary, we're adding to our dictionary beyond building equipment and worker, specifically for safety applications. Now we are able to detect hard hats and safety vests from the photos or videos. Some of the future directions that we would like to take our research to is object localization. In other words, when you look at the photo, you want to know where the objects are located, so that if you have a worker in the close vicinity of an equipment, and that vicinity is not large enough, or that distance is not large enough, you can send safety alert to the worker. Also, we want to do a saliency detection algorithm. In other words, you want to know, like I said, if you have a foreground, which is a worker, and a big building in the background, and your goal was to detect that worker, you should be able, your algorithm should be able to do that automatically. So that's the saliency detection. So here's some preliminary results so far from a multi-label annotation. In this case, as you see, we are tagging people, and then within each tag of a person, we can also identify safety equipment with personal protective equipment, such as hard hats and safety vests. So the idea here is that once you have a bounding box for a worker, if within that bounding box, you can also identify the bounding box for a hard hat and a safety vest, that means the worker is fully protected. And then if any of those bounding boxes is missing, that means the worker is not wearing either the safety vest or the hard hat. This is my student Nippon, like I mentioned at the beginning. This is all his research. So he has been testing on himself different combinations of a person with or without a safety vest or a hard hat. And we have also color-coded this, so in case a worker is fully equipped, then the color of the person box is green, and then if the person is missing an element, there is orange or red, depending on the level of safety of the worker. So that's all the presentation I have. Thank you very much for your attention.